Okay, should be recording. And let me hand over the floor to the seventh element to present their heliostat.
All right. Hello, welcome everybody. All right, this is Team 451M, and we're here today to present to you our heliostat design, the seventh element. Our team is comprised of the 7 engineers listed below: Alfredo Delgado, Brianna Renda, Charles Datko, Jarrett Cox, Malone Stanley, Rodolfo Rodriguez, and myself, Spencer Steinmetz. In the course of this presentation, we hope to outline our group's unique goals and abilities, as well as present a means of economically profiting off our work. Throughout the presentation, we'll outline key product specifications, as well as demonstrate operation of our product through videos and images. In addition, we'll demonstrate key features that make our heliostat stand out. Finally, we plan to provide insight into the design evolution of our heliostat, complete with exploded CAD views of our design and a final cost summary table. Our team was passionate about making a robust but straightforward design, minimizing complexities. We determined that we'd best be able to take advantage of this philosophy through our team's skill in developing 3D models and our ability to actualize them into 3D printed parts. This emphasis of simplicity and use of 3D printing goes hand in hand with our design's economic goals, as these parts are relatively cheap and allow our team to lower manufacturing costs. This subsequently aids in reaping greater net profits, thus fueling our team's economic engine. Our design stands out from the crowd through its simple but effective design, as well as through its minimal number of parts. This was achieved through the use of 3D printing to create complex parts that would otherwise require the assembly of numerous components that would each require multiple machining processes. Our mirror mounting subsystem that can be seen below acts to effectively demonstrate this benefit, as it encompasses a gear, mirror mounting platform, and a mirror actuating arm all in one piece.
Here we have a representative 3D model for our design. We have a mirror base, 2 motors, 4 gears, a motor mount, and motor enclosure case. As stated earlier, we have 3D printed majority of the design, which included the gears, the mount, the base, and the enclosure, all being 3D printed. We took inspiration from the 2021 Fall Group 4 design, which was a small-scale heliostat that specialized in accurate solar tracking at a low price. The accurate tracking allowed it to optimize the efficiency of the heliostat field by reducing losses of reflected light between the heliostat and the receiver. The actuation system helped accomplish this accuracy, as it utilized a motor and gear system to provide slow but precise movement of the heliostats. The motor placement allowed for both elevation and azimuth movements. The simplest subsystem was the base, which was just a square steel tube. The lower part of the posts were embedded into the ground to ensure that the module was secure, and to fit the restrictions in the MEC3 design class, we had to make modifications to this initial design. We wanted to emphasize simplicity, quality, and performance in our model.
We converted Group 4's design into a singular unit, which became the first iteration of our design, as seen in the image on the left. We kept the same actuation system design, which consisted of a 48-tooth partial gear and a 12-tooth small gear that drove the elevation axis, as well as a 48-tooth stationary gear and another 12-tooth small gear that drove the azimuthal axis. We increased the thickness of the vertical beam to provide better stability, since we had to scrap the crisscross design of the base for the 4-unit design, and also included a rectangular base plate on the bottom for further support. For the reflective subsystem, we increased the thickness of the mirror backing plate and made it the same dimensions as the mirror as well, again for better support. The final iteration of our design is seen in the image on the right. We scrapped most of the base subsystem, including the trapezoidal part connecting to the azimuthal gear, the vertical beam, and the rectangular bottom plate. All these parts were deemed unnecessary, as we'd be screwing directly into the base plate. Instead, we made a small cylindrical extrusion off of the azimuthal gear with a hole to screw into the base plate, which saved us in cost, the amount of material we'd be using, and time to manufacture. We altered the actuation subsystem by adding protrusions from the elevation and azimuthal gears for our limit switches. Additionally, we added holes on the side of the motor enclosure to screw into the motor mount, since there was nothing previously securing it. For the reflective subsystem, we reduced the amount of material used on the backing plate and integrated a crisscross design instead, because we concluded that that would provide enough stability and also put less stress on the gears. We also extended the backing plate over the corners of the mirror to provide a place for the mirror to slot into. We also combined the mirror backing plate, the two reflector supports, and the elevation gear into one part rather than having them be separate parts to make the assembly process easier. And then here we have some renderings of our final design from the front and from the back. It's a much more simple and more compact design than what we started with, which is what we were striving for with our concept.
Now to focus on more of the mechanics of our final design, along with the details and physical layout of all the parts. We can see here a partially exploded view of our full heliostat. It's split into three major sections here, each of which generally moves separately, yet in relation to one another. The bottom section shown separated out includes the base gear, which operates as the stationary grounding for the rest of the design. It was meant to not move at all and allows the metal motor frame section above it to move relative to it. This is done through the use of the interface between the larger gear on the base section and the smaller gear attached to a downward facing enclosed motor, which is part of the middle section. This interface between the gears allows for a roughly 360-degree azimuth rotation for the full design. The elevation rotation, on the other hand, is then provided by the interface between the other smaller gear shown, which connects directly with and is powered by another enclosed motor within the central section. This smaller gear moves the larger portion of the upper mirror frame section of the heliostat, which, as mentioned, is one multifaceted 3D printed part. This setup allows for a roughly 180-degree rotation for control of the elevation rotation. It is then also notable here that there are specific teeth on both of the larger gears, which are extruded slightly and help in making contact with switches located on the central motor frame section shown. As the middle and upper sections separated out here rotate in relation to one another, the interface between those extruded teeth and the said switches then occurs, which causes the switches to activate, and this is all necessary for aspects of the motor control. These extruded teeth which hit these switches can be seen on the right of the base gear as well as the upper left and right of the gear portion of the mirror frame part on the top. Now looking at a more fully exploded view of our design, it is more apparent now that we only have 6 central 3D printed parts, with the mirror frame section, as mentioned, all being one part, and then there being the L-shaped motor frame connected to it, which directly connects to and secures the two motors. The box-shaped motor mount above it, or motor enclosure above it, connects to the motor frame and has the purpose of simply protecting the motors while taking up minimal space. There's then the base gear part previously gone over, and of course the two smaller gears, which are identical to each other. Going over some of the off-the-shelf parts, there are 15 screws implemented for the design, 8 of which connect to the two motors, and then there being 4 for each motor. There are 4 screws also used to connect the motor enclosure to the motor frame, and then another 2 for the switches on the central section. And then there's 1 which connects the base gear part to the motor plate or whatever part it needs to secure down into. There are also 2 nut and bolt combinations used to connect the axle systems for each degree of rotation. This involved 2 axle and ball bearing systems respectively securing the motor frame to either the mirror frame or the base gear. This setup allowed for the mentioned parts to be securely fastened to one another while only clamping on parts which did not move relative to one another. This, of course, allowed for minimal friction and was only possible with the use of the ball bearings implemented. Overall, the mechanics and locations of parts detailed here were informed by the mentioned design philosophy of valuing simplicity and compactness.
The first major milestone for the project was the wind survivability test. For this test, we needed the prototype to be aerodynamically similar to our final design, but it did not need to have functioning motors in it. We tested our heliostat in 2 configurations: normal operating mode, which is shown on the left with the vertical mirror, and safety mode on the right, which is meant to protect the heliostat from severe wind. In normal mode, the heliostat was attached to a rotating Lazy Susan and placed 1.5 meters away from an industrial fan. This configuration was tested at 9.2 miles per hour and 11.9 miles per hour, with wind speed, each speed being tested for 5 minutes. Here in safety mode, the heliostat was tested using a Ryobi electric jet fan blower that was placed 10 centimeters away from the edge of the mirror. The prototype needed to withstand 134 miles per hour, which represents about 2 times the maximum recorded wind speed in Las Vegas. The final and largest milestone for the project was the laser reflection test. There were 5 targets placed throughout the lab that needed to be hit, with 2 of the targets having coordinates disclosed to us beforehand, and the others were given during the test. This first video represents the homing routine of our heliostat, done with 2 limit switches, and the heliostat was homed before attempting to hit each target. This second video shows the heliostat moving from its home position to the first target. These coordinates were given to us beforehand, and the correct angles were found using inverse kinematics. After rotation, we turned the laser on, and as you can see in the video, we were able to hit the center of the target.
In the development of our heliostat model, our group was tasked with remaining below a total budget requirement of about $110 US. The table on this slide showcases all the parts needed to recreate our design, the quantity of each part, as well as how much each part costs. The parts shown on this table include baseline parts, which are not included in our overall budget requirement, as well as unique parts that our group needed to manufacture and order. Without including the base parts, our group proved to meet the budget requirement of $110 by a pretty significant amount, emphasizing the overall efficiency of our design. Overall cost was also calculated in the event of mass production for our case 3000 models, with price cost estimated at about 80% of their original values using observed trends from our manufacturers.
This slide displays some of the dimensions of our heliostat. We were proud to be able to make a compact and lightweight heliostat that has all the functionality necessary. Due to the size of the heliostat, we envisioned that we would be able to maximize the land space given to us and have many heliostats working simultaneously next to each other. The majority of the 1.056 kilogram weight for the heliostat came from the 2 motors. Throughout the course of the semester, we put an emphasis on having a design that is compact and simple to manufacture. Excluding the cost of the base parts, we were able to keep our design within the budget by putting an emphasis on 3D printed parts. Our heliostat successfully withstood high winds as seen from the wind test, and also was successfully able to hit markers on the wall. This reflected a real-world application of redirecting sunlight to the towers. We are confident in the ability of our heliostat to be mass-produced and survive the vicious summer conditions in Las Vegas. At this point, we'll open up to questions from the guests.
Hey guys, this is Tom Singer from Northrop Grumman. Can you talk about why you went with a plan to 3D print parts versus something like injection molding?
Due to a lot of the complexity of certain parts, it was just found to be more feasible to 3D print them. This is seen with the mirror frame section specifically. A lot of the gear interfaces were rather specific to this part in hitting a lot of like the precision goals because we needed to hit that 0.5 degree angle precision. So given the costs and everything and the benefits of 3D printing and it being seen as a fit for our design, we decided to go with that for mass production.
Okay. Yeah, I'm something like the motor mount where you have the integrated, or not the motor mount, the mirror mount where you have the integrated mount and gear. I think that maybe makes sense. Something like your L bracket, however, or your motor housing, that sort of stuff seems like maybe that's a better candidate for something that's, you know, a relatively simple part that, you know, you're going to presumably make a lot of these, that a injection molding might be a better candidate. While we're looking at that, I know the load is mostly oriented in the strong direction on that L bracket, and that's good. I like the way that's designed, but I would encourage you to put a big old radius right in that inside corner to minimize any sort of fatigue, stress concentration issues from, you know, whatever side loading these things inevitably will get. But other than that, it's a structurally efficient design. I like it. What is the base of this mounting to? Right, so that bottom cylinder with the fixed gear on it. What is that mounting to?
In our testing, it mounted to a motor plate, which could be fastened into essentially a tripod fix. And this was done through a screw that connects to a heat set insert within our prototype.
So is that what you were, when you were doing the cost breakdown, is that what you're referring to as the base cost?
No, base costs were like essentially we were it's pretty much like the first half of this table. It's base costs were essentially baseline costs that didn't contribute to our final like budgeting requirement. These were like the costs provided to us for our design. But essentially the only pieces that don't go into our base costs were the 3D printed ones and the ones we had to order, which were like the heat set inserts and like things near the bottom of the chart over here.
Yeah, maybe to clarify a little bit more, in order to prevent those of us who are the course instructors from becoming completely overwhelmed with 18 different electronic systems, 18 different mounting systems, and so forth, 18 different mirror configurations, we imposed on the groups, for example, the electronics, the motor drivers, the stepper motors themselves, the mirrors, quick connect coupling. And so because we imposed those on the groups, we basically said, this is the cost to buy all that stuff. Put this in your budget. But that's, you know, basically what they call a base cost. That's something that you guys can't change because we forced you to make those choices.
Okay. So you're forcing them to make choices that cost $140 when the goal cost was $100 per module?
Yes.
Guys, you're killing them. Okay, so I think I understand that now. You'd mentioned on the slide where you had the dimensions, the mirror is, I think, something like 6x10, so 60 square inches. How many of these are you going to need to? I mean, your cost was per single mirror, right?
Yeah, that's correct.
Okay, and the goal was based on what, like cost per meter squared or something of reflecting area. I think I hazily remember that. And you guys have about 240 square inches of reflecting area versus like a 1 meter squared is like 40 times 40 is like 1600, right? So you're somewhere around an eighth of a square meter with your one reflector. Can you size that up? And if not, are you just going to have to multiply this total cost for one by 8 to get a 1 meter squared reflecting area?
I think, sorry, you can go.
I was just going to say that it is sizable, given a lot of the simplicity and the way we manufacture parts. On top of that, the system has a pretty high factor of safety, so you could just implement a much larger mirror. Of course, there'd be considerations.
Okay, so why is this your design then?
This mirror was one of the parts that was given to us and that we had to work with. I think that
This is part of Dr. Trom's base
in the
cost?
production run, it is in the base cost. Yes, sir.
Yeah, so that's another element of it. We didn't want, you know, square meter mirrors flip-flopping around in the lab, hitting people and stuff. So we we gave them much smaller mirrors to work with.
Okay, so the design is based around a test configuration and not the actual configuration. Is that what I'm hearing?
Yeah, I think that's accurate. Yeah, this is more about, can they design something that will cause a reflecting surface to be able to train on a target, right, with the laser coming down
Okay.
vertically, rather than like hitting the customer need of 1 square meter of collection area.
Okay, so okay, so this is more focused on the mechanism then. Okay.
Yep.
See, when you guys were testing, you'd mentioned that you were testing with a 12-mile-an-hour wind.
That was one
Yeah.
of the speeds for the industrial fan.
Yeah. So why 12 miles an hour?
Well, the industrial fan had 2 different speeds, a lower speed and a higher speed. So that's representative
So
of
you
the
picked
higher
your test
speed.
configuration based on what your fan could do?
We were given this fan. This is what we had to test with. So then we put the mirror vertically, which represents the largest wind load on the heliostat.
So how does that compare with what's actually required in service?
Well, we need a factor of safety of 2, which we tested that with the high speed, 134 miles per hour. Whenever the wind speed gets too high, our heliostat's not going to be functioning at the time, and it's going to go into its safety mode.
Yeah, and I guess I understand that. I maybe question whether wind speed multipliers correlate exactly to factors of safety, but I won't get into that now. But you know, for operating conditions, right? When you say, hey, we need to be able to operate in sort of, you know, a nominal wind condition that covers, you know, 80% or 95% or whatever of the conditions that you'll see during service, and then you go into your safe mode for 5% or 15% of the time or whatever it is. How does 12 miles an hour compare to, you know, the expected wind loading in service?
I would think it seems to be a little less than what the average wind speed would be in Vegas. I mean, it's definitely not going to be operating in anywhere near the maximum speed. I think wind speed in Las Vegas would probably be from 10 miles per hour up to 30 miles per hour. Maybe we want it to operate within that.
Mm-hmm.
So I should mention here as well that we imposed the wind test on them. So the fan selection and the speeds that we were able to achieve it came from me basically, and it was what we had in the lab, without, you know, for example, going down to the aero lab and asking Dr. Carroll or Dr. Abbott if we could put these things in a real wind tunnel. So to some extent, if the wind velocity is a little bit slower than what they might expect in service, that was again because we created the test for them and they just had to survive it.
Mm-hmm. And again, that's going to be strongly dependent on what the size of the mirror is anyway, right? The amount of force that you're reacting.
Yeah. These mirrors are, I would imagine, smaller than ultimately what these heliostats are going to be driving when we scale this thing up to full scale. The other thing I should mention, I'm glad, Tom, you're the only one so far that's picked up on factor of safety and wind speed multiplier aren't the same thing. I was waiting for somebody to say, hey, Trom, when you double the wind speed, it actually raises the force induced on these various surfaces by, you know, the square of the velocity, and nobody ever said that. So I said, okay, well, hit them with 140 mile an hour wind to try to replicate a 70 mile an hour maximum wind speed with a factor of safety of 2. And the students didn't complain. So that's what we went with.
There you go. All right, so that's all I've got. I'll kind of keep quiet for a little bit.
Right. We probably got time for about maybe one more question because the end time is 11:05. It's 11:03 now.
Hi, this is Lisa from Cummins. Yeah, thanks for your presentation. I thought it was really well done. And just wondering about the mirror. How easily is it replaced?
If you're asking about like taking it in and out,
Yeah.
given the flex of the mirror, we just opted for like a stationary, like a frame that doesn't move, and you can essentially just fold it in, and all the corners will kind of be like statically clamped down, which we found to be pretty doable.
So you're just kind of like bending things until they fit into place?
Precisely.
Okay. And when you remove it, would that damage the plastic 3D printed surface at all? Or have you looked into like assembly damage maybe? Or how many would be broken, I guess, if they're printed in a certain orientation maybe?
Yeah, at least in the short term, the PLA used was very sturdy for that part.
Yeah, and I think that the mirror itself was sufficiently thin and flexible that we kind of focused on moving it to fit the plastic or PLA, and not necessarily moving the PLA to fit the mirror.
Okay, so you didn't do any testing on breaking the any of the 3D printed parts, so like where they would be most likely to break? Any like testing for that?
No physical testing.
Okay.
You
Thanks.
could do finite element models for that in SolidWorks.
Ooh, do hand calcs.
Yeah, I was gonna say I would say against that actually, just because the 3D printed nature of it, FEA is really not great for that. I would think in my mind maybe doing physical kind of just testing of it, just although I'm not sure if the printing is going to reliably get the same failure modes, because something might print a little differently depending on orientation. But
yeah, that's maybe another interesting question. Like, what for that complex part, what orientation is that going to be printed in?
so the orientation that we printed in was so like face down. So the face that has like a normal vector going up was pointed to the ground. So it would just kind of yeah, so like that's how we printed it.
Okay, that's going to make those lugs significantly weaker.
Mm.
Yeah, you could test different print orientations and see which one's the strongest maybe.
Okay. So on that note, I hate to cut off a good technical conversation, but we have to move on to the next group, which was actually meant to start about a minute ago. I did drop their Zoom link into chat. So the panelists, if you are available, wouldn't mind making your way over to the next presentation. We'll wrap it up here with these guys. I want to just thank you guys for you're the first MEC 3 group to present, and it takes guts to agree to be the first one. And of course you field some of the questions that ultimately are, trauma imposed this on us, trauma imposed that on us, and you guys have to field those initially before the panel is sort of up to speed on the full customer needs. So I appreciate you guys agreeing to be the first ones. I think you did a great job. Very good presentation. Excited that you guys were able to hit the target. That was the coolest video I've ever seen. Like, you're like, we're doing it. And then like you zoom right in on the target. You guys are in the yellow. So that was awesome. So very good. And we'll hopefully see you in lab before the semester ends.
Awesome.
Awesome.
Thank you
guys
so
for
much.
coming.
Thank
Yeah.
you.
Thank you.
All right. See ya.